Okay.
So, good evening, everyone. It's my pleasure to welcome you all to our webinar today. This webinar is organized by the SP Student Chapter of Technical University of Crete. And our speaker for today is the Assistant Professor at the School of Production Engineering and Management of Technical University of Crete, Dr. Ipsakis Dimitrios. Thank you very much for your presence today. And the title of our webinar is Hydrogen Economy, Features, Technologies, and Future Perspectives. Now, Kostadina Kolipetsa will read a short CV of our speaker. Kostadina, the stage is yours. Thank you.
Thank you, Chrysula. Good evening, everyone. My name is Konstantina Kolipetsa. So, since 2019, Mr. Ipsakis is an assistant professor at the School of Production Engineering and Management with a specialty on the area of control systems with emphasis in renewable energy systems and energy saving. Mr. Ipsakis had his diploma and PhD in chemical engineering from the Aristotle University of Thessaloniki in 2005 and 2011, respectively. From mid of 2006 till 2019, he was a collaborating researcher at the Center of Research and Technology Hellas, Chemical Process and Energy Resources Institute. His research activities involve process modeling and simulation for energy, fuels and fine chemicals production, conceptual design and process control of integrated systems, techno-economic analysis, and final kinetic modeling of chemical reactions. A summary of applications involve the exploitation of renewables and light hydrocarbons towards biofuels, hydrogen, and power production through a flexible and autonomous operation. On the above areas, he has contributed with more than 30 publications on international scientific journals, one book and one book chapter, and more than 80 publications in national and international conference proceedings. Now, Mr. Anastou Dimitra, you can continue. Thank you.
Hello to everyone. Hydrogen economy is on the forefront of today's discussion in energy markets in Europe. Hydrogen is an energy carrier that can be used in vehicles. Applied examples include the brand names of Toyota Mirai and Hyundai Nexo, as an outcome of the fascinating progress made in fuel cell technology over the past 10 years. Other uses that go way back in time include oil refineries like hydrocracking processes, blended with natural gas for heat, power provision, ammonia production, space activities, and many others. On this introductory lecture, we will provide the basics for understanding the generic features of hydrogen. We will review its properties along with the established production technologies. Next, we will discuss how hydrogen can be integrated in daily activities, and we will close with a tentative economic analysis. And now, Professor Ipsakis, the stage is yours.
Thank you very much for the kind introduction. Before starting, I would like also to thank Professor Andreas Iotis, who is a close friend, close colleague. I would like to thank all of you guys that you have made tremendous efforts the past few years, as we discussed earlier. The Society of Petroleum Engineers, very good title. The student chapter has provided students, undergraduate, graduate students with, I think, all the facilities, the knowledge that they need at the age of 23, 24 to proceed with their studies on the field that you have already are working on. It's a big pleasure to be here. As the title says, today we will discuss the hydrogen economy. We will see features, technologies, and future perspectives. I will start with the outline of the presentation, just to give a bit of, let's say, details on what we are going to see in the next 40 to 45 minutes. I have prepared a series of slides that have basic stuff on hydrogen technologies. It is quite easy, I think, to be followed by engineering students. There are some details in some of this slide, and of course, it is a wide area of application of research that we cannot go into many details on this short time. So we will first begin with the physical properties and characteristics of hydrogen. We will then move on to the hydrogen uses in industry and today's market, and we will see that hydrogen is already out there. It is not something new. We will review the basic production methods, not only in small scale, but in larger commercial scales, as it is from 2000 and until now. A few stuff on storage and safety that sometimes it's the big concern, the big question on what happens with the safety of using it operating in hydrogen fuel cells, and I will close with two cases. The first is to see how hydrogen is being imported into vehicles. We will see a real case of Toyota Mirai, which is an actual vehicle that is on the road in Central Europe. And also, I have included a couple of days ago the hydrogen vision in Greece that includes also our island, Crete. So let's move now to basic stuff on what is hydrogen. And hydrogen is a clean alternative to natural gas and synthesis gas. Natural gas, we can say that is more than 90% methane, and synthesis gas is a mixture of hydrogen and carbon monoxide. Hydrogen can be produced in large scale from various sources like natural gas, biogas, refinery processes, and from water powered by renewable energy sources. Currently, we categorize hydrogen into three colors, but we will review them later. You can see the three colors here, but there are extra 4 colors. Burning hydrogen, of course, creates water. Hydrogen plus oxygen gives only water as the main product. There are no formation of oxides of carbon like monoxide or dioxide, or oxides of nitrogen or sulfur. At least they're not produced in high quantities when we are using clean hydrogen as the main component. Hydrogen can be transported through gas pipelines, as is the case with natural gas in big cities, in big infrastructures. However, the last bullet on this introductory slide is that economics are quite high already. Now, this is a basic picture of hydrogen that, of course, it's something usually being taught in schools. Hydrogen is a gas, of course. It is a light element. It has a very low density. You can see the different values here for boiling point, molecular weight, colorless, odorless, and other stuff that this type of light gases have. Two main features for someone that starts to work with hydrogen is that hydrogen is nearly everywhere. It can be found in 75% of all normal matter, but you cannot find it alone. You cannot find, for example, you can open a cave or a house or anything else, of course, I'm kidding, and find hydrogen. Hydrogen is found only in other substances. It is inside water, it is inside methane, methanol, gasoline, ethanol, diesel, alcohols, and so on, and all hydrocarbons. The characteristic of hydrogen of being a light element creates a big problem with leakage. Because it is light, it can go through small holes and can be expanded in the wider area, in the bigger area. Here at this slide, we can see the flammability limits of the percentage of hydrogen in air. it starts with about 4% and it ends up in 77%. This means that if there is hydrogen in an area outside and hydrogen percentage is lower than 4%, then nothing will happen. And also you can see the different temperatures here, but this matters very little as compared to the percentage of hydrogen. So in order for an accident to happen, we need to put hydrogen in a very small place that will increase in concentration. So I start with this, meaning that we should not be afraid all the time about if hydrogen will have a leakage. Of course, this doesn't mean that we should not have any safety measurements. Here are two examples of hydrogen flames. You can see that almost it is invisible. Here I have a picture of hydrogen flame on the left, propane flame, and also jet flame. So we can see that hydrogen flames are something between a propane and a jet air fuel aviation flame. So let's see some characteristic of hydrogen as compared to other fuels. I have selected here hydrogen to be compared at the higher heating value and lower heating value as kilojoule, as energy per gram. And also in the bottom half slide, I will show later the same table, but regarding its density. So we can see here that if I take the energy per gram of hydrogen, we can see that it is the highest value, either talking about higher heating value or lower heating value, as compared to methane, propane, and more importantly, to gasoline and diesel, which are the main fuels for transportation. You can see the difference is more than 3 times. If I compare now the energy density of hydrogen, meaning I will compare the energy per cubic meter, this means the energy density, I can see that hydrogen has a very low value as compared to gasoline and diesel that I referred earlier. We can see that these two motor fuels are about 30 million kilojoule per cubic meter, where hydrogen goes up to 4.500 million kilojoule per cubic meter, only if it is compressed at this value, at about 690 bar G. And this will be the case with vehicular applications. In order to have hydrogen in vehicles, I must have a tank filled with hydrogen at a pressure that reaches this 690 bar G. Even in this case, still gasoline and diesel, which are of course liquid fuels, have higher energy density. So if I have to compare something per mass, hydrogen receives a very a good credit point. Now, if I want to compare, I will put this somewhere around here. If we need to build a hydrogen society, we must consider hydrogen to take part as a leading role into 3 different things. Hydrogen should be used as transportation fuel. It should be used as an energy medium or a heat medium for domestic heat supply. And also it should be used as the main component, the raw material, to provide high added value chemicals. So in order to build something that is called hydrogen society or hydrogen economy, then hydrogen should take part in all of these 3 sectors: transportation, domestic heat, and also industry, chemical industry, refineries, and so on. In this way, if we can manage to build this hydrogen industry, we will first start with the production of hydrogen, and these are different types of pictures that we will explain later. Hydrogen should be produced through an economic way, for example, through renewable energy sources. It will be stored, and then it should be distributed either through tanks, either through big trucks, either through city pipelines, transported in order to be used in these three sectors that we discussed: the transportation, the industrial, household, and so on. So hydrogen society should have production, distribution, and uses as actual roles for hydrogen. What are the main hydrogen uses in today's sector? We start with power and heat generation. It can be used for power generation to supply energy and power to the grid. Hydrogen addition to natural gas, for example, blending hydrogen to natural gas pipelines. This is something that, at least from what I have heard, because I'm not an expert, says that 5 to 10% of hydrogen can be introduced to the gas pipelines. And this hydrogen can provide heat for buildings and industry. In industry now, it is used for ammonia production, steel production, synthesis gas, and refinery processes dealing with hydrodesulfurization, hydrocracking, hydrogenation. And as we will discuss at the end of today's lecture, we will see that it can be used in hydrogen vehicles. Currently, but this number is increasing, hydrogen accounts for about 10% of global hydrogen consumption if I take into account the energy production. Now here is, let's say, a spider diagram or spider picture that I found on the internet, and I really like to use. We see here at the heart of this diagram the hydrogen. At the beginning, as we said, we need to produce hydrogen. We have, for example, renewable sources, nuclear power. We can take hydrogen from methane reforming, coal gasification. We'll discuss about this. We'll take a minute to see what these processes and technologies refer to, hydrogen electrolysis and so on. Storage either in vessels, in liquid form, gaseous form, or in metal hydrates. And then we have the uses in buildings, gas grids, transportation, synthesis of fuels, and so on. Here, based on what we discussed earlier, here are some numbers regarding the potential hydrogen production starting from 2020 and for the next 30 years. In 2050, a lot of let's say government, European Union, some other global organizations say that in 2050, we will have to build a society that will be net zero, meaning no carbon emissions. You can see different sources of the material that I've been using on this lecture, so you can check also some other numbers. We can see here the different colors as they refer to refining, industry, transport, and so on, that they will increase the hydrogen demand over the next 30 years. These are two scenarios. The right-hand side refers to no carbon emissions, where the left-hand side means that we will have some carbon emissions, but it will be as less as possible. And we can see that in both scenarios, in order to achieve this low or net zero emission, we need to increase hydrogen production. And not only increase hydrogen production, but use hydrogen in these different sectors that we can see. I will go directly to the 2050, where we will see that hydrogen is proposed to be used in, we'll start with a bigger, with industry, refining, transportation, power, synthetic fuels, and also different chemicals like methane and others. Now let's see if hydrogen can be used in more fascinating, let's say, applications like hydrogen in space, in islands, or even in a laptop. Here we see a rocket sent from NASA to the outer space. Liquid hydrogen has played an important role because it was used as a supply fuel instead of batteries. So liquid hydrogen or gaseous hydrogen was something that NASA is being using for many decades now. Now, this is a very strange, looks like a big bird. This is the Helios from the Greek word describing sun, unmanned aircraft that utilizes a fuel cell system that it is powered by hydrogen, and this hydrogen is provided by solar power. So during the day, solar cells can operate these unmanned aircraft, where at the night, the fuel cell can generate electricity with the hydrogen that is being produced. Here is a portable, like a power bank, operate with a small tank of hydrogen. And also, Manvit in Iceland has designed facilities for hydrogen production through geothermal energy. So these are actual applications and not something that is science fiction. When I started my PhD, Professor Konstantopoulos created and not created, but I would say invented something that it is called the hydrosol reactor or hydrosol plant. Here is a big tower. Inside this tower is a reactor that concentrates the solar power provided by different concentrated solar panels. It has, through this concentration of power, the temperature increases in very high levels, more than 750, more than 800 degrees. And in this way, we can split water. It is a very efficient way to produce hydrogen from solar water splitting. And this plant, this idea, the hydrosol plant, you can see the different details here, has received numerous awards for Professor Konstantopoulos, a Greek professor in Thessaloniki. Other sectors include food, metalworking, welding, flat gas, medical, and so on. Now, let's go a bit quickly on the hydrogen production routes. And I say quickly because if we need to stay at each of these technologies, we may need one seminar alone. Steam reforming is the basic hydrogen production route. Methane and water are being put together in an endothermic reaction to produce CO, CO2, and hydrogen. This is the main hydrogen, I'm repeating, route for today's market. An alternative is the partial oxidation of methane that provides CO, hydrogen, and of course it is an exothermic process. Here are some very few details. It is steam reforming takes place in commercial, in large scales. It is something quite known. It is a catalytic process, so a lot of effort, a lot of research is being doing there for providing good catalysts. Coal gasification is another way. Coal, besides other components, has a big percentage of carbon. Through water, coal gasification can lead to CO and hydrogen as well. Power electrolysis, it's, let's say, the green process where water and electricity are being combined in order to provide hydrogen. You can see that there are no emissions besides oxygen. Now, for an electrolyzer, I will say a few words, if you don't mind. An electrolyzer is I will say an electrochemical machine or an electrochemical reactor. It has two compartments. I will start with the proton exchange membrane. We have the anode, the membrane, and the cathode. Water, through the provision of electricity, you can see the reactions over there, over here at this table. Water is being split into hydrogen and oxygen in the form of ions, protons and oxygen ions. Through the membrane, only the protons can pass to the other side. And of course, I need electricity in order to split water into these components. The difference with the alkaline electrolyzer lies on the membrane, on this diaphragm that allows these hydroxide ions to pass from the cathode to the anode. So another way, this is the main way to produce hydrogen from renewable energy sources. So if I have an electrolyzer with water inside, I can power the electrolyzer and split water into hydrogen and use it. Another renewable energy source can be, for example, wood or other substances or other things that are thrown away in agricultural industry. And pyrolysis means, I have used the example of methane. Pyrolysis means that I provide heat only without air and split components, for example, into carbon and hydrogen in the case of methane. In this way, pyrolysis is like splitting a component into its main constitutions. A very futuristic and fascinating hydrogen production refers to the photosynthesis for hydrogen production through biological processes. This is still in progress, but if some of you have more, let's say, interest on this process, they can review it into numerous videos that exist. It is a good technique, however, it still needs a lot of time to develop and provide a commercial application. Here we have the different colors of hydrogen. Does hydrogen have a color? Well, the answer is yes. We have gray hydrogen when hydrogen is being produced from natural gas steam reforming, blue hydrogen when it is produced from steam reforming, but the CO2, the carbon dioxide that is being produced, if it is captured, then we are talking about blue hydrogen. And green hydrogen is the process of electrolysis as it is powered by renewable energy sources. Four other colors that I find quite funny is black hydrogen from gasification, pink when electrolysis is powered by nuclear, turquoise pyrolysis with main source natural gas, and yellow hydrogen is process electrolysis powered by solar. However, these are the main three colors that if someone asks you to refer to them, you can say that we have gray hydrogen, blue hydrogen, and green hydrogen. You can spend some time here seeing this information and depict it on your mind of what each color represent. Now, for every kilo of hydrogen produced, more than 10 kilos of CO2 are being emitted to the atmosphere. So this means that with gray hydrogen production, I emit a lot of CO2 to the atmosphere. Also, if I use the gray hydrogen production, this means that I will use natural gas, which is quite expensive, at least the last 12 months with different geopolitical reasons. We can say that natural gas prices are increased. 1 kilo of hydrogen requires more than 4 kilos of natural gas. So if we need to proceed with hydrogen economy, my opinion is to move to blue and green hydrogen. And here are some cost relations to the processes that I referred. We can see here that gray hydrogen is about $2 per kilo, and this refers not to the actual production cost, because there are also other costs regarding transportation, storage, and so on. This is, let's say, a basic production cost from gray process, $2.2, 2.9 if I include carbon capture and storage, and 4.5 if I move to the green process powered from solar and wind energy. So we can say that we need to spend at least 2 to 3 times more money in order to move from the conventional methane reforming to green hydrogen production. Here are some other calculations on the cost regarding steam methane reforming without CCS, with CCS, autothermal reforming, coal gasification with and without CCS, biomass gasification, and so on. This figure tells us that the current hydrogen production from steam methane reforming is polluting the environment with CO2, but it is still the lowest regarding the cost implications. So if we need to move to a more green society, hydrogen society, we need to spend more money. And this figure also has something similar to tell us. Now, these are the more or less things that I have said to you in the previous slide. No need to refer to them again. I need a couple of slides to make an introduction to the PEM fuel cell, because I will use this technology, which is the reverse of the water electrolyzer, because I will move to the case of the Toyota Mirai. Now, what is a fuel cell? In the fuel cell, again, I'm having the electrolyte, the anode, and the cathode. Here, I provide hydrogen to the anode. Hydrogen, it is being split into hydrogen protons that can pass through the membrane to the other side, where is the supply of air, and electrons are passing through an external electric circuit. Passing electrons, moving of electrons, transportation of electrons, you can say, we can use any other word, means that I have electrical current. Electrical current means electrical or power or energy production. This is what happens at the anode, the splitting of hydrogen into protons and electrons, and this is what happens at the cathode, oxygen, along with protons and electrons provide water. So from the one side, I have hydrogen, from the other, I have air, oxygen is included in the air, and what I take at the outside? Water, which is quite, let's say, a peaceful product, and also electricity. There are different types of fuel cell, the alkaline, the proton exchange membrane, direct methanol, phosphoric acid, molten carbonate, and solid oxide. What is the difference between these categories? The mobile ion, meaning what it is passing through here through this electrolyte. So here is the different mobility of ions for the different categories of fuel cell. Here are other characteristics regarding the temperature. Take a note on the solid oxide fuel cell that goes up to 1000 degrees. So this means that this type of fuel cell can provide not only electricity, but also heat in very high quality, can provide high quality heat in high temperature. Phosphoric acid, as an historical note, is, if I remember correct, were among the first that were built for space applications. Hydrogen storage, we can store hydrogen in physical or in material-based types. In the physical in the physical type, of course, we can store hydrogen as compressed gas or cold cryocompressed with low temperature. And also, if we lower even more the temperature, we can store hydrogen in liquid form. Material-based means that I have to build a material that will store hydrogen inside this material. And these materials are called metal hydrides. This technology is called metal hydrides. It has high efficiencies, but still the physical based are more commercially available as we speak. So these are different absorbents. They have very difficult names for someone to remember. Here is what hydrogen storage looks like in gaseous form, and this is how hydrogen is being stored in liquid form. Some, let's say, comparison between gaseous, liquid, and solid hydrogen storage. Basically, the gaseous storage is commercially available. For the liquid storage, we can find it commercially, but it is still costly. We need very good insulation dewars. These are the dewar tanks, as they being called. Here you can see in the first case that hydrogen is being stored up to 700 bar. Here you can store it in atmospheric pressure, but at very low temperature. And this is something that I said earlier, that we are in the, let's say, in R&D development. There are a lot of things to do in order to make it public. So after this introduction, I have given you, I know, a lot of details, but I have not gone very far into details for the different technologies. So I have selected something that I think that you will like. This is an actual car that it is not under design, but it is operating, as I said in the beginning, in Central and Northern Europe. This is a Toyota Mirai, which is a fuel cell vehicle that uses hydrogen as the main fuel, the energy medium that generates electricity and powers the vehicle. We will see everything that we need to know inside this car. This information is not classified. You can find it on the internet, and I have I think here, yes, I have here the manual for you to review it. The TFCS, the Toyota Fuel Cell System, has a very high energy efficiency as it is compared with our conventional vehicles, internal combustion engines. It has zero emissions because, as we said, fuel cell only emits water when we have hydrogen from the one side and oxygen from the other side. This is how the inside of this vehicle looks like, and we will see each of these parts. Underneath the seat of the driver, it is the fuel cell stack, which gives a maximum output of 155 horsepower if you need to compare it with actual values of your car, your parents' car, your friend's car, and so on. So underneath the seat of the driver, it is the fuel cell. The motor is, as in conventional vehicles, it is in the front of the car. This is an electric motor because it is driven by electricity provided by the fuel cell. It is an electric car. It is not operating on batteries, as we know, for example, Tesla and many other vehicles operating with batteries. This car operates with hydrogen and an electric motor. The battery is at the back side, down the passenger's seat. It is a NIMI, a nickel metal hydride battery, that has the same application, stores energy and receives energy during the braking of the car. Of course, since we have an electric motor, we need some boost converters in order to increase the voltage provided by the fuel cell, and also some control units, because it is a very expensive car. We need to take into account humidification, how oxygen, hydrogen are being supplied to the fuel cell. Now, let's see what is this yellow thing here, yellow tank. This yellow tank is the high pressure hydrogen tank, which is between the drivers and the back passenger seat. This hydrogen tank receives hydrogen at about 700 bar. How this car operates, we start with step one. Air is being introduced through these holes from the car, goes up to the middle of the car, inside the fuel cell. Here is the fuel cell stack. Here we have the hydrogen pressure tank at the point that I mentioned earlier. So hydrogen with oxygen are being combined in order to provide power, electricity to drive the motor, along with electricity from the battery or to the battery. And how hydrogen is being refueled, we will see it later. And the last part is that what it is emitting from the car, which is basically pure water. As Toyota claims this, we can see how the inside now looks with two passengers. This is the battery, the hydrogen pressure tank, and the fuel cell. It provides a low center of gravity. It has good aerodynamics. The technology of the fuel cell has gone a long way. It is quite one of the, let's say, best technologies of fuel cells in cars. 370 cells, giving a horsepower of 155. And here also some auxiliary components like pumps, circulators, converters, and so on. And received some awards as first world class in humidification. Toyota has worked for more than 20 years on building this car, starting from early 2000 up to 2016 or 17. Here are different information regarding what has changed from the 2008 to the 2018 model. It is lighter, the fuel cell is lighter, it provides more power, it is more efficient, it is better as the first, let's say, version. Here is how the operation inside the fuel cell operates. We discussed about the membrane, the oxygen and the hydrogen inlet, basically the same principles as more than 10 slides earlier that we discussed. Here is how something also for describing what has changed from the 2008 to the today's version. We can see that it is more efficient if we have the fuel cell here, the boost converter, the motor, and the battery operating in a better way as the previous model. Now, if we need to fill hydrogen in hydrogen station, the hydrogen fuel cell station, the refueling time is about 3 to 4 minutes, which is actual a low period of time. If I have an electric car and I need to go from Thessaloniki to Athens, I will need to stop about 2 to 3 times to charge my vehicle and spend at least 30 minutes per charging. With hydrogen cars, I can go from Thessaloniki to Athens with one full tank. One full tank of this vehicle has about 4 to 5 kilos of hydrogen that gives an autonomy of more than 500 kilometers, which is the distance between Athens and Thessaloniki. And we will see the average price is about 60 to 70 euros for charging, for fueling my new hydrogen vehicle. The hydrogen vehicle, as these figures describe, is that they can start at very low temperature, especially in countries like Canada and Northern Europe. Since time, I think I have 5 more minutes, I will pass some slides. I need to compare hydrogen fuel cell with electric and petrol vehicle, that I think that you may have some questions. Hydrogen fuel cell vehicle starts at 60,000, electric at 21, petrol at about 8. So these are average prices. The range, you can see it here, which is similar for hydrogen and petrol or diesel vehicles, lower range for a low budget electric vehicles. In my opinion, if you ask me, I don't think that hydrogen vehicles need to replace electric vehicles. In my opinion, hydrogen and electric vehicles can replace petrol and diesel vehicles. So both of them are needed towards building a green society. Other cars is from Hyundai Tucson, Honda Clarity, Honda and also Hyundai Nexo. You can see the different what its company provides to the driver. Here is an overview of the Europe with green are actual hydrogen stations. We have in Europe more than 100 hydrogen stations, most of them are in Germany, that they can refuel with 700 bar your hydrogen vehicle. In the upcoming months, they claim, as the European Union, that more than 6 million of vehicles will be able to switch to hydrogen and power, and you can power and fuel and charge and fuel your hydrogen into these stations. Of course, we need more in order to provide hydrogen vehicles to the world. If someone asks if hydrogen will still will be used in the near future, I have the example of Germany, which is a country with a good economy, and we can see that they have an increase in hydrogen service station and also a big increase, a tremendous exponential increase in hydrogen demand in Germany. So this means that hydrogen will be alive for the next decades, as these numbers claim. So the price for filling stations in a hydrogen station is about 12.85. So basically, more or less, it's the typical value that I will give for refueling my gasoline car. And closing, I will give two slides regarding the hydrogen vision in Greece. As the General Secretary for Energy, Ms. Alexandra Zdoukou, stated a couple of months ago, is that with the EastMed gas pipeline, the EU hydrogen supply backbone can be provided in long term. In 2040, there are strategies for building hydrogen facilities powered from renewable energy sources that will give an income of more than 1.6 billion euros per year. So this is a good number. Hopefully it is correctly calculated, and some others say that in 2050 we will have a return of 10 billion euros per year only from hydrogen production. A big project that is underway is the White Dragon in Kozani, the Western Macedonia. total investment of more than 8 billion that will give hydrogen of this amount powered by solar and wind energy. And the last now, very good information, good news for Crete is that Crete has been selected as a hydrogen valley from the Clean Hydrogen Partnership, along with some other regions like Bulgaria, Ireland, Italy, Turkey, and Luxembourg. This is how in Adriatic area the hydrogen distribution is claimed to take place in the next few years. So in Crete, we will have this hydrogen valley, hopefully in the next few years. I will close with something that one of a good professor, a good friend, Professor George Marnelos had in his slides, is what Jules Verne at the Mystery Island claimed. You can see here that it said at this book, I believe that water will one day be employed as fuel, that hydrogen and oxygen, which constitute it, used singly or together, and will furnish an inexhaustible source of heat and light. And we can see that Julius Verne, more than 150 years ago, had water powered from sun to provide solar hydrogen. So this means that hydrogen was on the mind of earlier scientists and science fiction writers, but we will see that his vision is already taking place. So that was all for me. Sorry for taking 3 or 4 minutes as I see here on my clock. This is everything that we discussed, and these are some interesting videos for someone to revisit after I will make the presentation public.
Thank you very much, Dr. Ipsakis, for this very interesting presentation. Let us now move on to the Q&A session. We will begin with the questions in the chat. I will read them to you and you can answer. So the first question is, what color type is the hydrogen produced by biomass pyrolysis and biomass gasification?
Okay. I will go to the respective slide. So the question was with coal?
What color type is the hydrogen produced by biomass pyrolysis and biomass gasification?
Okay. Interesting, because I don't have a color for that. So biomass is considered a renewable energy. So if biomass gasification or biomass pyrolysis is being used, they can say that it is green, powered from renewable sources, which is biomass included. The different colors for gasification and pyrolysis strictly refer to this source of coal and natural gas, which are fossil fuels. So I haven't seen something describing only biomass powered production for hydrogen.
Okay, thank you. The next question. Currently, does it cost more to refuel a car that uses hydrogen or a conventional one?
Okay, we can make the calculation together. Now, a hydrogen car needs 5 kilos, okay, 5 kilos of hydrogen. A full hydrogen tank requires 5 kilos of hydrogen. Times 12.85, you can make the calculation. I think it's about 65 euros, right? So 65 euros in order to fully charge my hydrogen car. My gasoline car, which is a Toyota, by the way, needs about 50 liters of gasoline, with a price of 1.9, I need about, I don't know, 95 euros for the same autonomy on the road. So a hydrogen car requires less money to be fueled, but requires 2 times more to buy it. Okay, so if you make these calculations, you can see how much fuel you will require and see if your investment on hydrogen vehicle will pay forward for the next years.
Yes, very interesting. So the next question. Methane gas hydrates are very widely known. They are quite stable under atmospheric conditions. Hypothetically, hydrogen can be stored in the same form. What is your opinion?
Can you repeat the first part regarding the methane?
Methane gas hydrates are widely known. They are quite stable under atmospheric conditions.
Hydrogen is also stable at atmospheric conditions. The only problem with hydrogen is to provide a closed tank in order not to be leaked outside.
Okay.
For example, there are facilities, laboratory facilities that have methane tank, methane gas, and hydrogen gases, concentrated, of course, in some inert gas like nitrogen, argon, helium, and so on. But they are both stable.
Okay.
Sorry to interrupt. I believe that the question refers to the possibility of storing hydrogen within gas hydrates, in the context of gas hydrates, in a similar fashion as hydrogen is stored within metal hydrides.
Okay. I don't have an answer for that because I haven't worked on that. Now I understand what gas hydrates.
If I understand correctly the question, but I think this is the concept.
I need some time to find the answer. Maybe the guy or the girl that has this answer can mail me and give a proper answer tomorrow or in the next few days.
Okay, thank you very much. Let's move on. Good evening. Thank you very much for the excellent and very important presentation. I would like to ask a question about the safety of the hydrogen tank, which is at the pressure of 700 bar in the event of collision.
Okay. Thank you for this question. Can I use a video for that?
Yes, of course.
Okay. I think this explains everything. It is a very, sorry. It's 1 minute video.
Hi, I'm Jeff Goldmere, GE's fuel guy, and I'm Simon Blakey, the IHS Market Energy.
I wouldn't expect the, okay, so.
Safety systems in place, it's extremely unlikely that these vehicles would leak much fuel, and even less likely that a leak would result in fire. The controlled simulation you're about to see shows the result of the failure of one system, the pressure relief device. Though experience with natural gas has shown that a failure of the pressure relief device is extremely rare, the results of such a failure would appear like this. In this demonstration, fuel was purposely leaked and ignited by an electric spark in both a car fueled with hydrogen and a car fueled with gasoline. The hydrogen tank empties in less.
I hope that this answers the question. This is also my first question when I start working on hydrogen. What happens with hydrogen tank is also there are some others. You can see also this video. I will put it, but it requires more, a couple of more minutes. This is a bullet inside the hydrogen tank at very low time proceeding. if you go until the end of this experiment, you can see that nothing happens. So this means that hydrogen tanks are safe to use, because when hydrogen moves to the atmosphere, hydrogen is in a very low concentration. The atmosphere has oxygen at very high percentage. So only if you find hydrogen at a closed space, then there will be a problem. Outside, safety measurements say that a hydrogen car will explode less possible as compared to a gasoline or a petrol engine.
Okay, thank you. And the next question. According to your opinion, can low temperature fuel cells survive on the market due to their sensitivity on CO impurities and their water management difficulties?
Yes, low temperature fuel cell can have a problem if the hydrogen fuel has CO at the range of, if I remember correct, of 50 ppm. However, most fuel cell technologies and companies say that you should use clean hydrogen. So if you are using clean hydrogen, low temperature fuel cells like the PEM fuel cell is already in the market. I don't see any problem of getting this type of fuel cell available in higher scale. But if you are going to fuel your fuel cell with a mixture of hydrogen, CO, and CO2, then I think you may need to change the type or the anode catalyst that you are going to use. This is something that R&D departments are working on.
Okay. Next question. Is the water that is emitted from a hydrogen car stored later for later usage, or does it come out from the exhaust?
It comes out to the road, like spilling
as
a type
liquid
of
or
water.
as a gas?
Like in a liquid type, like spilling a small cup of water.
Okay. Okay, and the next question. Combustion of organic fuel at temperatures above 1100 Celsius leads to a sharp increase in the emission of extremely toxic NOx. Is it safe to use hydrogen in this connection?
Use hydrogen where? I couldn't understand the question.
So the question is, combustion of organic fuel at temperatures above 1100 Celsius leads to a sharp increase in the emission of extremely toxic NOx.
Yes.
So I think in the combustion of organic fuel, yeah.
Okay. I don't understand the connection with hydrogen. You mean if I am using...
He writes in the chat as a fuel for vehicles.
Using, for example, organic fuels in vehicles instead of hydrogen or other petrol and so on.
Maybe the person can unmute himself or herself to ask the question to help the discussion, if possible, please.
Oh, yeah, it's possible. Good evening.
Good evening.
Yes.
Good evening.
I'm glad to meet everyone. And of course, I'm asking about fuel. Fuel for turbines for vehicles and so on.
Nice meeting you. You are discussing a way that in vehicles we will power them with a fuel, not hydrogen, not petrol, and
No.
so on, but
Sorry.
with another type.
I mean hydrogen as a fuel for vehicles, for turbines. I mean, which uses on heat power electric stations, for example. Because
okay.
here we achieve a temperature on the level much more than 1,100 degrees of centigrade.
Okay. Something that I intentionally didn't provide to my presentation is that in my opinion, I don't think hydrogen is a good choice of in combustion engines. I don't think we should produce hydrogen in order to use it in a big power station, in combustion internal engines and so on. I think also that EU policy do not provide solutions for hydrogen in power plants. I think hydrogen is more meant to be used in transportation, in industry as a raw material. I have seen some, let's say, results of hydrogen to be used in as a combustion fuel, but there are some issues with some radicals that are being created during the burning. But I haven't seen a lot of effort on internal combustion with hydrogen only. I don't know if I help you with my answer.
Thank you. Anyway, thank you.
Thank you. So now let's move on. What makes green hydrogen much more expensive, and how can we make it cheaper?
Okay, green hydrogen requires renewable energy sources. So let's take the simple example of photovoltaics, wind generators. So these are, okay, expensive technologies, but they are planned to be less costly in the next decade. But the most costly equipment is the electrolyzer. The electrolyzer, as we took a note on this slide, requires a catalyst at the anode, catalyst at the cathode. These are expensive materials. It is produced now in large scales in 1 megawatt, but the price is about 2,000 per kilowatt, 2,000 euros per kilowatt. So if you need to build a 1 megawatt powered electrolysis, you need more than 2 million. So the electrolyzer is expensive in green hydrogen production. And this, of course, the capital expenses, the equipment expenses are higher as compared, for example, to steam methane reformer that operates in a catalytic reactor that is known for more than 50 years.
Okay. So can you comment on hydrogen storage using alternative methods?
Probably we are discussing about metal hydrates, the material based.
I don't know. Maybe, yes.
Okay. Yes, because the conventional one is the physical one, compressed or in liquid form. Metal hydrates, as we said, has a high efficiency. You need to provide some heat or remove heat during the hydrogen storage, sorption or desorption, as it is called in these processes. The efforts of the society, the research society, lies on let's say building these infrastructure of these different metal structure. If research society tries to find metal infrastructure that will sorb and desorb hydrogen in low time and in high quantity, then I think that the material based can be compared to the physical based. But still, I think physical based storage is more available in today's market. But research is taking place very good research, and I still that they will have very good results with commercial cases in the next 3 to 5 years, in my opinion, of course.
Okay, thank you. Next question. Would it be possible to use part of the produced hydrogen to produce more?
Sorry, come again?
Would it be possible to use part of the produced hydrogen to produce more?
Okay, we produce hydrogen. What do you mean by using some part to produce more?
Maybe the person who asked the question could help.
Yes, of course. I mean, using a portion of the quantity that we have produced and use the energy to electrolyze more.
Okay, so you are meaning, let's say that I have a solar panel. I split water into hydrogen and oxygen, store hydrogen, and use hydrogen in a fuel cell to produce electricity? A cycle like this, you mean?
Not exactly. We produce hydrogen.
Yes.
We store it.
Yes.
Let's say we store it in 2 compressed
Cylinders, tanks, yes.
And we use one of them to create more hydrogen, to produce more hydrogen.
I cannot understand how to create more hydrogen with hydrogen. What do you have in mind?
The one tank will go to cars, for example,
Yes.
for immediate usage.
Correctly.
And the other tank will be used to redo the electrolysis so that we can get hydrogen.
Yes, this is maybe, okay. The electrolysis requires water and energy.
Mm-hmm.
Okay, so let's see it here. So water and electricity provides hydrogen. So this hydrogen can be stored in cylinders and used in cars, as you correctly said. Okay. Hydrogen cannot go back to electricity and water through water electrolysis. Hydrogen can give electricity in fuel cells, which is the opposite operation.
Okay.
I can use hydrogen in fuel cells to provide electricity, but my point is, since you are going to have electricity at the beginning to provide hydrogen, then you should stop here. If you are using hydrogen to provide electricity again, then you are using, let's say, you are losing efficiency here.
Okay.
It's a type of a cycle. For example, let's say in a typical example, I eat and then store some food to eat it again. This is the part of the hydrogen storage. If I store food to create more food, then it means that I have to spend more energy to create more food. So this means that I'm spending more money.
Okay, okay, understandable. Thank you very much.
But you can make a type of cycle like this at this application of this type of drone. This type of drone, the Helios, uses solar energy to create hydrogen. Solar panels operate the system, and during the night, the hydrogen stored is used in fuel cell as a battery to keep it going. And in the next day, solar panels receive sun, operate the system. So it is a closed cycle. In this application, yes, you can store hydrogen and use it again because you don't have other option.
Okay, thank you very much.
Thank you. So now let's spend 10 more minutes on the Q&A so as to not exceed our time limit. The next question is, if you include hydrogen in a hybrid power solution, is there an ideal energy mix to optimize cost?
It's a difficult answer. So using hydrogen with another type of gas, the question says.
In a hybrid power solution, yes, I think that they mean that.
So probably hydrogen, methane, hydrogen and natural gas is a good energy mix. Hydrogen in the form of synthetic gas, carbon monoxide and hydrogen is another energy mix that can be used. Hydrogen and CO2, which is CO2 greenhouse gas, is also another energy mix because CO2 and hydrogen can provide methane, can provide methanol. So you can combine these two as well. So yes, hydrogen can be combined with specific, of course, types of gases.
And how does that optimize the cost? Does it?
You need to make a combination of the energy cost and the environmental cost. So methane is cheap. It's cheaper than hydrogen. If things go as it goes the last 12 months with methane increasing prices, then hydrogen may be comparable in the production cost with methane. Okay, this is the one part. Now, combining, for example, hydrogen and methane in burning facilities, for example, in domestic heat supplies, this means that I lower carbon emissions from methane because I use hydrogen at its position. So I lower the environmental impact. I don't have much CO2 to the atmosphere, so I don't pay a lot as CO2 tariff. So in this way, yes, there may be an optimization, very difficult problem with this methane gas and hydrogen gas mix.
Okay, thank you. Next question. What is your opinion about hydrogen produced by reforming, for example, biomethanol?
That was my PhD thesis subject. I used to work on methanol reforming for producing hydrogen. I have a very good and high opinion for that. Methanol can also be a hydrogen carrier. There are race cars. You can see, for example, Toyota, Daimler, Chrysler. They are using a methanol-powered car. And methanol is the main fuel in fuel cells, the direct methanol fuel cells. So yes, I have a very good opinion on that process.
Okay. Are there any case studies in return on investment in hydrogen capital expenditure benchmark period to create value? What is a benchmark period to fully recover upfront investment and generate a fair return?
Can you, because I lost you at the beginning, can you repeat?
Yes, yeah, of course. Are there any case studies in return on investment in hydrogen capital expenditure benchmark period to create value?
Yes. If we are discussing about hydrogen production from steam reforming, the payback period is, I think, less than 5 years. If we are talking about hydrogen production from solar and wind power, I think the payback period reaches about 10 years. Of course, there are different factors. For example, where you are planning to build your solar park, wind park, you need to have a lot of solar irradiation, wind energy, and so on to produce more hydrogen. These factors are quite sensitive, so I think that the payback period is about 10 years for green hydrogen production, but still I'm not sure about this number.
Okay, so let's answer the last two questions. The energy required to produce hydrogen is much greater than the energy that hydrogen releases. Why not use the energy directly into batteries and electric motors?
Good question. It is exactly as this person said. We are using energy to produce hydrogen and then hydrogen to produce energy and so on. So we are losing efficiency. If we power batteries, then we will have electric cars. This is, of course, acceptable. My, let's say, different opinion is we cannot use the next 10 or 20 years only electric cars. I think we should use both hydrogen cars and electric vehicles, because electric cars have, okay, low price, but what happens with the battery? You need to recycle battery, you need to change battery maybe after 7, 8 or 10 years at a cost of, I think, more than 1,000, 2,000 euros. So yes, I'm losing energy for creating hydrogen, but I'm building something that will last more outside on the road.
Yes, that's clear. Okay.
So this is, let's say, my type of view for hydrogen and electric vehicles. Both are needed, of course. It depends on the driving, let's say, character of each one of us. For example, I don't want to stop every 100 or 200 kilometers to charge my car and spend 30 minutes.
Yes, understand.
There might be, might have, for example, another opinion.
Yes, for sure. So the last question. What are some of the biggest challenges facing the widespread adoption of hydrogen as a mainstream fuel source?
What are the main
challenges?
The first is, of course, building electrolyzers for hydrogen production at low cost and in high efficiency. This is one, if we are talking about green hydrogen production. The other one is to build good carbon capture and storage technologies and processes in order to produce hydrogen in the blue. I will put it on the slide. To build CCS, carbon capture and storage technologies of high efficiency in order to capture CO2. But the third big challenge is to find actual applications in order to use hydrogen, not only in industry, because hydrogen is being used in industry, but we need to use hydrogen in transportation and domestic heat. These are the big challenges in order to provide facilities all over the cities. And of course, this is something that EU policy and EU governments should work together in order to find, let's say, the space for hydrogen in daily activities.
May I also ask you, isn't hydrogen transfer from the production place to the consumption place an important bottleneck?
Exactly, yes. Exactly.
You didn't mention that. This is...
Yes. I forgot that distribution is also a big factor. I will use this slide. This is in Japan. Japan has an island structure. They have a type of ships that they are trying to move hydrogen from the one side to the other. Even I have read some papers of delivering hydrogen to Australia in the form of ammonia. They are using hydrogen inside the ammonia in order to transfer it through ships in other places and then use it as hydrogen and so on. So yes, logistics exactly, Andreas. Good to mention.
I'm
is
asking
important.
because there is a lot of discussion regarding the production of green hydrogen in countries where there is, a lot of renewable energy, like sun or wind and so on, and then transporting it through pipes, or I don't know, pipelines towards other countries. What is your feeling about this? Is this possible, given the technology of today?
I discussed 4 or 5 years ago with some people in Middle East that they had experience on gas pipelines, and they were quite certain that hydrogen can be blended in a portion of 10%. I don't know. Probably yes, it is feasible to blend it with hydrogen. My question is, can hydrogen inserted in gas pipelines at 100%? What happens there?
Yes,
Because the leakage is important.
Yes, because
that's an
then you
issue.
introduce, sorry to interrupt you, then you introduce another limitation. If you need to have also natural gas, then you need to buy from that country both natural gas and hydrogen.
Exactly.
Okay, so the country should be a producer of natural gas, of both natural gas and hydrogen. And this is away from the carbon-free concept of economy. So it is 90% carbon-based fuels. Okay.
From what I see here at the hydrogen station in Europe, I see a lot of hydrogen station in this central part that is being produced from renewables. So we'll see how this will be expanded. That's challenging.
Okay, thank you.
So, thank you very much, Mr. Dr. Ipsakis, for this very interesting presentation. And thanks to everyone for the questions and for attending today.
Thank you also for the invitation and your help.
Thank you very much. It was an excellent presentation. Thank you.
Bye-bye, everyone.
Have a good evening.
Have a nice evening. Thank you very much, Professor Ipsakis.
Thank you, Andreas. Have a good night, and also all the other guys. Bye.
Bye, everyone.
Thank you very much. Bye-bye.